Hi, and welcome to Compute Session 333, Scaling Network Performance on Next-Generation EC2 Network Optimized Instances. My name is Antti Dury. I'm a Senior Product Manager with Amazon Web Services, part of the EC2 Compute Cloud team that manages the infrastructure instance types. I'm joined by...
Hi, I'm John Pangle. I'm a Senior Product Manager with AWS as well. I'm part of the VPC and networking team with the product management team.
Thanks for joining us again, and let's take a look at the agenda for this session. So in the first part of this session, I'll talk about how we're innovating for our customers in terms of EC2 network optimized instances. I'll go a little bit into the journey of how we got to launch network optimized instances, why we launched network optimized instances, and then go over our offerings and new announcements this week. In the second half, John will talk about EC2 innovation on the networking front, how we have launched SRD, Scalable Reliable Datagram for EFA in the past, and how we're expanding this capability to all EC2 instances. So starting with a little bit of history to explain how we got to network optimized instances, we launched EC2 in 2006 with a single general purpose instance, M1, and we thought customers would just run more of these instances, but instead we learned pretty soon they needed different types of instances to best run different types of workloads. In 2008, we launched our first compute optimized instance, which offered less memory per vCPU than the first one, so we changed the memory to vCPU ratio. In 2009, we launched our first memory optimized instance to address workloads that needed more memory per vCPU. By 2013, we started to innovate on our infrastructure implementation to offer customers more of the cores they were renting on these instances in a technology called Nitro. And we launched the first instance based on Nitro in 2013. It was called C3, and it offloaded network processes from the host CPU. In 2014, we continued to innovate, and we launched the C4 instance, which also offloads EBS storage processing from the host. And this was the first instance we developed in collaboration with Annapurna Labs. And the EC2 team was so impressed with the Annapurna Labs team and the technology that AWS decided to purchase the company. And as history shows, this has led to a lot of innovations in the years since then. Part of this innovation, by 2017, we got to the point where we offloaded the remaining infrastructure processes from the CPU, including control plane and I/O functions. So we launched a new hypervisor and launched the full Nitro system. And at this point, we're able to offer all the CPU cores to our customers. This was the C5 instance. And the following year, we got to the point where we were able to launch the first network-optimized instance. This was the C5N. And it was made possible by really years of innovation in Nitro, as you have seen. And it was the first instance in the cloud that offers 100 gigabits per second networking for a variety of customer workloads, which we'll talk about in a little bit. We ended up launching a full portfolio of instances. But before going there, the first question is, why do we need network-optimized instances? As customers continued to migrate workloads to AWS, they told us that some of the workloads needed more bandwidth, and they were bottlenecked on the network performance. They were not able to use all the cores and all the memory of the machines they were renting, and they asked us if we can do better in terms of utilizing these instances. So what types of workloads are customers running on these instances? Let's go over some of these. So the first category is network virtual appliances. This includes workloads like next-generation firewalls, virtual routers, load balancers, DDoS machines, NAT gateways. For these workloads, customers need both high bandwidth and high packet performance. These are both important. The second category of workloads is distributed compute and HPC. A lot of times, these workloads run on clusters with EFA networking, low latency clusters, high bandwidth. This was one of the initial workloads that were targeted when we launched C5N in 2018, and a lot of customers are using it for HPC. And it was so successful that we ended up launching a full portfolio of HPC instances, some of which were announced at AWS here. Customers also use these instances to run communication workloads, 5G UPF, for example. Another category is data analytics. It includes a lot of types of data analytics, but in general, these are workloads that read a lot of data from S3 or data lakes and then generate business insights, for example, customer recommendations, and just a variety of different computations that customers perform. Customers also use network-optimized instances for CPU-based AI/ML for training and inference. When they don't need to go all the way to a GPU, they use network-optimized instances such as C5N. They also run a lot of in-memory databases. Example of these are Aerospice, Redis, Memcached. These are workloads that use a lot of bandwidth between the nodes in a cluster when you have reads and writes, and they use especially a lot of bandwidth when nodes are added or removed from the cluster and they need to rebalance the data. Customers use these instances also to run high-performance file systems, which need both high networking and high EBS performance. I'll talk a little bit about that later. And then most recently, we've heard from customers that they're using these instances for high-density containers. As they decompose their workloads into microservices, the components that use more bandwidth need to move to high networking instances when customers are trying to pack more containers per instance. Next, I'll go over the existing portfolio of network-optimized instances. So up until recently, until this week, our portfolio offered 100 gigabits per second. As I mentioned, we launched C5N in 2018. It was very successful. Customers told us they wanted to run other workloads on high networking instances. And the following year, we launched M5N, R5N instances, and also instance storage variants of these. So we offered a pretty broad portfolio of instances to run all the types of workloads that you have seen on the previous slide. And we look to continue to innovate to offer customers the best performance and price performance. And in 2020, we launched the C6GN instances, which put together Nitro innovation and Graviton innovation. So this was the first Graviton-based network-optimized instance. It offers the same 100 gigabits per second as the rest of the portfolio, but offers up to 40% better price performance and 40% better packet processing performance. And we've seen a lot of customers optimize their workloads to transition to Nitro to save on cost and take advantage of some of this improved performance. So we've been offering a pretty broad portfolio of instances to support a variety of workloads, but we asked ourselves, what's next? Talking to customers, trying to get the slide. Yeah, so talking to customers to get feedback, we learned that as they continue to grow their deployments on AWS, they are looking to scale the network infrastructure throughput. A lot of times, these instances implement the connectivity to customer networks, and you're looking to scale this up. Customers are also storing more and more data into S3 and data lakes, and as analysis gets more complicated, they need to analyze more of this data to generate customer insights. So they asked us, how can we help them reduce the time it takes to read this data from S3? Some customer workloads, such as network virtual appliances, need high packet performance. And customer asked us, how can they get higher throughput for smaller packets for these workloads? And finally, until today, customers had to choose between high networking performance and high EBS performance. Some customers told us they had workloads which needed high networking but also needed high EBS. And then customers who are running high or EBS-intensive workloads told us in some cases, for some workloads, they want high networking. So we looked for an opportunity to address all these feedback points in the next generation instances. Introducing the 6th generation of EC2 network-optimized instances. They were announced earlier this week, and they're generally available today in several regions, so we're looking forward for customers to try them out, give us feedback. We launched CMR variants, so all 3 memory to vCPU ratios. These instances offer up to 200 gigabits network bandwidth so customers can accelerate how fast they read data from Amazon S3, for example. They offer higher, up to 50 gigabits per second burst network bandwidth for workloads that scale out on smaller instances. And a lot of these workloads use baseline bandwidth, and then they need to burst sometimes to higher bandwidth. So this is for some smaller instance types. Finally, for workloads with higher network, which need higher packet performance, these instances offer up to 2x higher packet performance versus previous generation. These are also the first Amazon EC2 instances to offer both high networking and high EBS performance. I mentioned earlier that some workloads need both. They offer up to 80 gigabits per second EBS bandwidth and up to 350K IOPS, input-output operations per second. This is the highest EBS performance in EC2. The new instances are ideal for high-performance file systems, databases, big data analytics types of workloads. And for workloads that need low-latency instance storage, they offer up to 2x larger instance storage. Let's see what customers are saying about the new instances. We've enabled a few customers before the launch. So we worked with Arctic Wolf. It's a cybersecurity technology company providing managed threat detection and response services. They had a chance to test the C6IN instances, and they saw up to 30% increase in packets per second for their specific workload. We've also worked with Intel to partner and make sure that networking ISVs can take advantage of the full capabilities of the CPUs used in these systems. They're based on Intel Ice Lake CPUs. And these CPUs offer new instruction sets for cryptographic and vector processing. So when you order an application, a networking application from the Amazon Marketplace, you want to make sure it gets best performance on these instances. Based on initial testing, Intel has seen up to 60% better IPsec performance on these instances, over 7x better AI inferencing for AI/ML workloads, and 2.8x better connections per second for networking workloads such as Nginx HTTPS. So we're very excited with the initial feedback from our customers. We're looking for more customers to try out these instances and provide feedback. So I've talked a little bit about how we innovated in our network, in our Intel CPU-based network portfolio. Of course, we also continue to innovate on our Graviton portfolio. The Nitro system enables us to offer better security, state-of-the-art security, and at the same time offer better performance across CPU, networking, and storage. And we found that when we offer end-to-end AWS solutions with Nitro plus Graviton, we're able to offer customers the best performance and best price performance. So how did we leverage this in our next generation instances? C7GN was announced earlier this week in Peter's keynote. Is the first EC2 Graviton instance to support 200 gigabits per second network bandwidth. This is 2x higher bandwidth than previous generation instances, C6GN. Similar to our Intel portfolio, they offer up to 50 gigabits per second burst bandwidth for smaller instance sizes. A lot of customers scale out their workloads on smaller instance sizes. They offer over 50% higher packet performance versus C6GN. This is the highest packet performance across EC2 network optimized instances. And because we offer smaller instance sizes on Graviton when compared to C6IN, for example, these instances will offer 2x higher packet performance per vCPU. Overall, the C7GN instances offer the highest aggregate and per vCPU network performance across our portfolio. And they will really be suited or ideal for workloads that are the most demanding network-intensive customer workloads. All this network performance is enabled by the new Nitro V5 card. This was also introduced earlier this week. So these cards are designed using the latest generation I/O interfaces. They use PCI Gen 5. They use DDR5 to make them to offer higher throughput and make them more responsive. As a result, we're able to lower latency by 30% just at the Nitro V5 chip level. And we do this with 40% better performance per watt. You can see 3 of these cards in the C7GN server. They're red colored, so each CPU gets a Nitro V5 card. C7GN instances are powered by the latest Graviton 3 eCPUs. These were also introduced a little bit earlier this week. They offer up to 35% higher vector instruction performance versus Graviton 3 instances, and these are the highest performance Graviton instances in AWS. So we want to make sure customers get sufficient performance and they have no limitations on these instances in terms of CPU performance. The C7GN instances are available in previews, so we're looking forward to customers to apply for preview, test out the new instances, let us know what you think. We're pretty excited about the full portfolio, both the Intel instances and the Graviton C7GN instances. I'll now pass it on to John to talk about other areas we're innovating in to scale performance on AWS.
Awesome, thanks, Antti. All right, so Antti just took us on a journey of innovation leading up to our latest network optimized instances on the Ice Lake and the Graviton platforms. I'd like to talk to you about Nitro and some of the software that helps enable this journey. Nitro innovation at its heart has allowed us to offload a lot of critical functions from the instance and onto dedicated cards. These cards are like Lego blocks, which allow us to piece together different instance configurations to meet different workload demands. With this innovation, we were able to iterate faster and launch new capabilities sooner. On this slide, you can see examples of the various functions we have offloaded from the instance and purpose-built for you, including security, storage, and hypervisors, and my personal favorite, networking. This innovation allows us to improve your security posture and overall performance with these lightweight building blocks. Today, I'm going to specifically focus on some innovation we have enabled with the networking Nitro Controller. This Nitro Controller was custom built for AWS Virtual Private Cloud Networking. With this Nitro networking card, we're able to offload a lot of critical networking functions from your server. From a networking perspective, one of the first innovations this led to was the Elastic Network Interface Adapter, or ENA, interface. ENA is a network driver that binds to the Nitro card and allows us to use the same driver across many different instance types and sizes, allowing you to use the same driver on different networking bandwidth instances. Like other building blocks, this reduces the load on the server by moving these critical functions to dedicated hardware. ENA specifically enables VPC networking functionality, including encapsulation, stateful firewall rules for security groups, and local and remote networking configurations for your network, to name a few. Additionally, it ensures you achieve consistent performance and predictable networking performance from instance to instance, no matter what availability zone you happen to be in. In addition to these core features, it has also enabled us to build enhanced networking. Enhanced networking is purpose-built capabilities to enable higher PPS and low latency applications to perform better. Enhanced networking works with single root I/O virtualization, which enables dedicated physical hardware to work directly with the virtual functions such as ENIs. It's a method of device virtualization that provides higher I/O performance and lower CPU utilization compared to traditional methods. Finally, as Antti has highlighted, Nitro has enabled us to expand our instance networking capabilities with Ena to up to 200 gigabits of network performance for our core instances with the announcement of the C6IN and the C7GN. That's up to 100% greater throughput than previous generations and a heck of a lot more than the original M1 instance. To achieve 200 gigabits, 2 network cards are required to actually do this to achieve the full network bandwidth. However, even a single network card is capable of delivering well over 100% or half, or well over 100 gigabits or half of that instance network bandwidth. This is purpose-built to enable bursty performance in your application. Before the C6IN and the C7GN instances, multiple network cards were already enabled on AWS. We supported these on the accelerated compute instances such as the P4D and the recently launched Trainium1. However, these workloads rely on a consistent network performance and require consistent 100 gigabits per second from each network card. Through software, we're able to achieve a bursty performance where necessary with our core instances and a consistent performance where critical with our accelerated computing instances. Additionally, as you can see here, with accelerated computing instances, we're able to achieve up to 1,600 gigabits per second of network bandwidth with the latest generation of TRN1 instances, which were announced earlier this week. And as Dave said, I think more to come. These accelerated computing instances take advantage of the Elastic Fabric adapter, another networking innovation enabled through Nitro. Launched in 2018, the EFA is a purpose-built interface for machine learning and HPC applications, such as weather simulations, computational fluid dynamics, solving natural language processing models, or performing machine learning image recognition. These workloads rely on parallel computing strategies, which spread out the effort over multiple different nodes for more efficient processing to reduce the time to completion. Libraries such as Nickel for machine learning and MPI for HPC are middleware packages that allow for collective communications across these multiple nodes to work. These communication libraries work directly with libfabric, which is a core component of the Open Framework interface, which is a library that defines and exports user space APIs directly to the network card. In this case, what that means is that libfabric enables kernel bypass, allowing direct communication from the application to the network layer, as opposed to traditional networking applications that have to go through the kernel, right? That EFA is powered by a custom AWS protocol, scalable, reliable datagram. We've talked about SRD a lot this week in Peter's keynote and Dave's leadership session. SRD is a purpose-built native AWS protocol designed for high bandwidth, low latency applications. With all these components combined, this networking stack here allows for the application layer to directly communicate with the EFA in this case, which eliminates milliseconds of latency from your applications. When you're working in microseconds, those milliseconds that you're able to shave off is huge. So let's take a look at how SRD works. SRD works by using an ECMP, or equal cost multipathing-like packet spraying mechanism, an advanced congestion control built directly onto the network. By distributing the load across many links, we can better balance our traffic and throughput and deliver significantly more packet throughput on a much more consistent basis, or more formally, we're able to significantly improve P99 and up latencies. Additionally, with the deep knowledge of our network, we're able to detect congestion and blockage sooner, and we're able to route around this and avoid any issues over longer periods of time. Tail latency in particular is important when it comes to distributed applications, where the next step in a pipeline may be blocked if you can't execute until the previous step is complete. So even if you have a great P50 or your normal latency, your median latency, your application may not be able to advance if you're blocked on your last packet. This is the same technology that's enabled in IO2 Block Express. EBS IO2 Block Express, excuse me. And then if you'd like a deep dive into, I don't know if you can see that, deep dive into SRD, we do have a technical paper out there that goes into all of the details there as well. So again, if you tuned into the Monday Night Live session with Peter DeSantis, you may have caught his wheel reference. SRD is the conical wheel of our data center, built for one purpose, and in this case, HPC and machine learning applications, but useful with so many other applications. Customers have continued to ask for new capabilities in this space. Databases require high bandwidth, can at times be network congested. Uncompressed media streams are becoming more data and network intensive as they become larger. And file system specifications call for higher throughputs. File systems today are limited by the number of mounts or connections they can have. And as we continue to increase our total instance network bandwidth, customers with these challenges are less capable of leveraging the total network bandwidth that we just talked about due to their applications and/or networking limitations that might prevent them from using 100 gigabits per second or 200 gigabits per second. Or they have to use multipathing, but that can be more challenging, adding complexity and overhead to your process. So, as a purpose-built technology, we asked ourselves, how do we leverage this protocol SRD more broadly and optimize it for other network-intensive workloads that generally rely on TCP and UDP, most of your applications? TCP and UDP are great on the open internet, but specifically in the solace of our data center, they have their downsides. Like our HPC and machine learning instances, our general purpose instances reside in our large data center, and it has the same opportunities to take advantage of our deep knowledge and our multipathing capabilities of SRD. So we asked ourselves, how do we take advantage of SRD with TCP and UDP? But can we replace TCP and UDP again like we did in that previous stack for EFA? How does it handle packet delivery? And how do applications work with SRD and ENA? How would it handle packet delivery for applications expecting in-order delivery? Finally, how do we make it simple and easy to use for customers? And one key thing to note here, with SRD for EFA, we actually deliver packets out of order and rely on the upper layer applications to put those back in order. So let's revisit the problem with traditional TCP flow hashing before talking about how we are improving it with the Ena Express. So with traditional routing, a single connection flows across a consistent network path, as you can see here. Sometimes large flows from multiple different senders end up hashing on the same path, even in a large over-provisioned network. This can result in network switches in the path becoming overloaded and struggling with all this additional throughput. This is commonly referred to as head-of-line blocking, where that congestion will slow you down as your packets are continuing to transmit across the network, as you can see here with this yellow circle. This network congestion will result in packet delays and potentially packet drops, which will cause TCP to retransmit and back off your total throughput. This TCP congestion control is generally a good thing, but it was built for the broader internet over longer distances and for general purposes, big and small. Normally, when this congestion happens, packets are dropped, retransmitted, and TCP backoff happens. This is very common with incast scenarios, where multiple senders are transmitting to a single receiver, and the receiver becomes overloaded with throughput. The receiver says slow down, but it's often too late, and packets get dropped. This results in increased latency for your application from the network and delays up the stack. Aside from congestion, failures do happen. This is what you see depicted here with this red circle. In this case, traffic stops flowing, TCP doesn't respond well at all, and you have to wait for a timeout. Once this timeout happens, you'll reflow hash, and you'll find another path through the network, but in the meantime, your application is stalled. So, introducing Ena Express. In partnership with our Annapurna labs, we expanded on SRD, and we rebuilt it specifically for ENA. And we made it transparent to TCP and UDP. This means you don't need to make any changes to your application to enable it. To get started, it just takes a simple configuration on a per network card basis. You can do this when launching an ENI or with a modify ENI command once it's attached. It works with all operating systems, but optimized for Linux and Windows as well. And it uses a lot of the exact same technology as SRD with the EFA under the hood. Functions like ECMP, packet spraying, and congestion control continue to work on Ena Express. However, for ENA, we do automatic packet reordering for both TCP and UDP. TCP, as you guys know, expects packets to be delivered in order, and it does not handle out-of-order packets. While UDP doesn't necessarily expect them in order, we saw an opportunity to make this work more efficiently for you. So how does it work? Your application will still operate with TCP and UDP. That won't change. But SRD will automatically establish an SRD connection after detecting compatibility on another EC2 instance. SRD acts as a wrapper, encapsulating and decapsulating packets at the Nitro level, while hiding a lot of our network inefficiencies from TCP and UDP at the stack above. This allows for faster retransmits and a reduction in any sort of network tail latency or jitter. With the Ena Express, we want to highlight a few key performance benefits, as well as the simplicity or functionality that makes this very, very easy to use. First, Ena Express increases your single flow bandwidth 5x from 25 gigabits per second from 5 gigabits per second to 25 gigabits per second. That's a 5x throughput improvement that is really important for large distributed systems as they continue to grow. Additionally, we've shown up to an 85% improvement on tail latency in in-cast benchmarking scenarios, particularly under high load. Like I said, Ena Express works with a simple configuration. It's a single API call or a click in the management console. And additionally, it's completely transparent to TCP and UDP. Finally, Ena Express supports same AZ traffic, meaning you can use it for applications running across different subnets and different VPCs with different network segmentation. All of these benefits are great for workloads like file systems, in-memory databases, and live media encoding. With file systems specifically, we knew there are OS limitations that prevent multiple connections. Often customers are limited to a single connection and unable to send more than that 5 gigabit per second of traffic that is our current bottleneck today. With the Ena Express, we were able to unlock a lot of potential here. But there's an explicit trade-off we are making with the Ena Express. Through the processing we're doing on the Nitro card, we are consuming some of the resources there, and when it comes to high PPS and P50 intensive applications, we recommend evaluating Ena Express before enabling it within your application. So how do you get started? First, you need to launch 2 instances in the same availability zone. You need to enable SRD on your network interface. And like I said, that can be done with a simple modify or attach network command. And it's that simple. Now, there is one caveat. Because we are encapsulating and decapping your packets, we do ask you to adjust your max MTU if you're using jumbo frames down from 9001 down to 8900. If you do want to use UDP as well, you'll need to enable that explicitly within that same API call or command line or console click, excuse me. We wanted to ensure this was explicit. In addition to enabling SRD, because UDP can be a bit tricky here, a lot of custom-built applications will actually have UDP reordering built into them. And because we were going to do that for you, we wanted to make sure it was explicitly chosen on your behalf or by you, the customer, when you enabled UDP. Once you've configured your instance, you can load iPer for your favorite benchmarking application on both instances, and you can start sending traffic between the two. What you should be able to see from there is up to 25 gigabits per second of traffic flowing between your 2 instances. So with some of our testing, and we did a lot of it, we tested in-cast scenarios, some of the common opportunities we saw with EFA. In this case, we had multiple senders in a single receiver, and we measured different parameters as we ramped up the amount of traffic the receiver could handle. This was done in comparison between Ena and Ena Express, so we could explicitly see the improvements with TCP. What we wanted to evaluate was, in fact, would we see better performance as a result of the SRD working on the Nitro card level? So what you see here is total throughput between Ena and Ena Express as we ramp up load on the receiver side. What you'll see is that the flow rate of Ena Express starts to diverge for the positive. In this case, higher is better, around 50% of traffic load on incast. This is a typical problem with TCP and incast. And it's usually caused by TCP's inability to handle incast scenarios. Now on the right-hand side, under load, TCP starts to back off a flow rate. And at times, we'll have to drop it to retransmit packets. That's what you're seeing here on the right. TCP over Ena starts seeing orders of magnitude of higher retransmit rates than TCP over Ena Express. This is because SRD is inherently better at responding to this incast network congestion and traffic. In this case, lower is better. In addition to testing throughput and packet rate, retransmit rate, we also wanted to test tail latencies as I said before. For those not familiar with tail latency, it's the round trip time for a packet to do the last X percentile of traffic. And in this case, it's the last 1% of your packets being sent or the last 0.1%. Like tail latency, or excuse me, like throughput, tail latency starts to see a noticeable improvement with Ena Express as the load continues to grow. Here we see up to 50% improvement on your tail latencies for your RTT for P99. When we extend our tail latency out to 3 nines, we see an even greater performance boost of up to 85%. And as you add more nines, it gets better. So this previous tests were all benchmarks, pure performance tests with FlowGrind to test basic networking performance. But we also wanted to evaluate this against various real-world benchmarks and scenarios. Redis from our Amazon Elasticache is a widely popular RAM-backed key value store benchmark. We tested it with a targeted number of queries per second. So in this case, we had a single client reading from 8 servers with a key size of 64 bytes and a value of up to 256 kilobytes. Then we zoomed in on the latency at 5,000 queries per second, which is indicative of a fairly high load, approximately 80 gigabits per second of throughput. And as I mentioned before, we can actually get up to 100 gigabits per second throughput. So 80 gigabits per second is 80% of total load here. What you see here is that we zoom in on our tail latency. The delta grows between ENA and Ena Express. This is due to the delays and the retransmits that occur with traditional TCP, as I talked about earlier. With Ena Express, we see a 44% improvement on 2 nines. And Peter noted 44% improvement on 4 or 5 nines the other night. And as he mentioned, we are partnering with Elasticache to make this available soon. Another use case where we see these benefits is with live video and media encoding. Encoding, due to the large transaction or frame size. Today, media encoding can be processed with EFA or more commonly on-prem, where customers tend to run dedicated, redundant, and parallel streams to ensure reliability. Before today, it wasn't possible to do this with Ena. At a high level, video encoding works by sending uncompressed video files between 2 servers, with one server having the raw file and server 2 reformatting it into some other new format for different forms of distribution. As a few data points of reference, a single uncompressed high-definition flow operates at about 3 gigabits per second. A 4K or ultra-high definition flow operates at 12 gigabits per second. Before Ena Express, this flow rate wasn't possible with Ena for a single stream, as we are limited to 5 gigabits per second. Additionally, video operates at 60 frames per second. What this means is that all frames must be received in order in less than 1 divided by 60, or 16.67 milliseconds, or else it's lost. There's no getting it back when you're live broadcasting. And finally, as a performance requirement when testing various scenarios or benchmarks, we must ensure that there are no frame delays over a 24-hour period to ensure consistent performance. So what we're looking at here is a graph with time and hours on the bottom on your x-axis and latency on the y-axis. This red line is that magic number, 16.67. And as you can see, I've zoomed out a little bit here. First, we look at average or transactional latency for a frame in that 1/60th time frame. For the sake of representation, I actually averaged out some of these numbers to simplify it. Otherwise, you'd see approximately 86,000 data points. And that wouldn't really work well with PowerPoint, so sorry. As you can see, on average, that yellow line is good. We're never crossing that threshold, that red line. But when you look at the last frame rate, or your P100, what you see is hundreds and thousands of late frames, failing any broadcast requirement to have 0 late frames over a 24-hour period. So obviously, we wanted to test this with Ena Express to see the performance benefits we could do here. Again, you have time and hours on the bottom and latency, transactional latency on your y-axis. And we tested Ena Express with HD flows. What you'll see on average, again with this blue line, is that the average packet is delivered on time. But as I mentioned before, this isn't that important. So let's take a look at the maximum. As you can see here with this yellow line, the maximum latency, no packet ever exceeds that threshold. All packets are delivered in full and on time, thanks to the power of Ena Express. Now, obviously, we wanted to take this one step further. As I mentioned, HD flows, we wanted to look at 4K flows. And 4K flows, like I said, are 12 gigabits per second, or approximately 4 times bigger. And we couldn't possibly do this with Ena because of our 5 gigabit per second flow limit. But we already know, like I said, we already know we won't be able to do that on Ena, so there's no comparison. So again, we look at average latency. And you can see here it's a step change up, but this isn't too surprising because our transaction size is 4x bigger. But where the real important part comes in is the maximum latency. As you can see here, we have a step change up overall, but all frames are delivered on time and in full over 24 hours. That's over 86,000 frames and 1 million gigabits of data. This will change the way media encoding works in the future. So this is awesome. This is all well and good. How do you know it's working right? How do you know you've set it up properly? So we wanted to make sure we are launching with monitoring tools as well, directly integrated into the Linux ETH tool to enable real-time evaluation and troubleshooting. We also wanted to ensure customers had visibility into their TX, or their transmit and receive packet counts. Additionally, we wanted to make sure you had visibility into the number of SRD eligible packets you could send. With these metrics, you can compare SRD transmits versus SRD eligible to determine if you're actually running into an issue worth troubleshooting. Likewise, you can use these metrics to compare to your traditional networking counters over a period of time to ensure you're properly using SRD. Additionally, we will expose an SRD utilization metric. This metric is a percent SRD utilization intended to inform you of a potential scaling cliff. When your percent utilization runs high, it's time to scale up or out your instances to ensure you have the available resources for SRD. Finally, we wanted to include a Boolean configuration metric here to ensure you know that you have SRD set up properly. Excuse me. So, in summary, Antti covered the network optimized instance innovation. We're continuing to scale here with up to 200 gigabits per second in our instance portfolio. The Intel CPU-based instances are generally available now, and we invite you to sign up for the preview for the C7GN instance with that QR code on the top right. And with the Ena Express, it's available in all commercial regions. Available on the C6GN 16XL instance today, with many more coming soon. And if you'd like, please check out our launch blog in the bottom right-hand corner to learn more. Additionally, there are some other sessions here highlighting Nitro innovation and some of the things we're doing there, the Elastic Fabric adapter and how that works, and some of our leadership sessions where we go into broader things on compute and networking. And that's it. I'd like to thank you all for your time, and please complete the survey session in the mobile app, and I think we'll have a few minutes here for Q&A as well.